Okay, students, today we will be concentrating on these few topics: Reimer, Tiemann, Kolbe-Schmidt reactions, freeze and Claissen's rearrangement with mechanism. Now let us first look into the portion which we had done last day, that is electrophilic substitution reaction of phenols. Now what is electrophilic substitution reaction? Now in the ring of the phenol, that is phenol, as you can see, the negative charge keeps on resonating. So this is a kind of electron rich species. So if something has to attack on the ring and there is a substitution happening on the ring, okay, then what can come? It cannot be an electron rich species. Okay, it has to be an electron deficit, or you can say Lewis acid. Okay, or where there is an electron deficiency, those types of species or molecules can come and attack. Or you can say the other way, phenol can attack the species which are having electron deficiency. So what do you understand by electrophilic? Electrophilic means electron liking. So some compound, some species, some molecule which has a deficiency of electron, or definitely those type of molecules will be having a liking for electrons. So the ring substitution reaction which is included here is not nucleophilic, rather it is electrophilic, means something which is electron deficit and which is having a liking for electrons. Okay, so all this portion that I have shown, you will find that most of them are all of them are nucleoelectrophilic substitution reaction. Let us go to the first one. Okay, what do you see here? Okay, it's a Reimer-Tiemann reaction. So first thing, we have taken phenol here. It can be a substituted phenol, where it can be a methyl group or a methyl group in any of this position. Now the reaction is happening like that it is having the product is what? It's a ortho hydroxybenzaldehyde, means an aldehyde group is being substituted in the ortho position, and since aldehyde group is the more prior group, priority is more compared to hydroxy group, the name goes like this, ortho hydroxybenzaldehyde. Okay, so what is Reimer-Tiemann reaction? Reimer-Tiemann reaction is an organic reaction used to convert a phenol to an ortho hydroxybenzaldehyde using chloroform, a base. What is the base? Base can be a sodium hydroxide and acid workout. Okay, so what is an acid workout? Means an acid takes and proceeds the further steps to the final product. The mechanism begins with the abstraction of proton, okay, from chloroform. So chloroform, the base, from the chloroform, the base abstracts a proton, okay, to form trichlorocarbon anion, a negative charged carbon species, which spontaneously loses a chlorine ion to form a neutral dichlorocarbene. So we are getting a neutral dichlorocarbene. Any carbene is an electron deficit species. Okay, it's an uncharged, but it is not having octet. It is having 6 electrons in the valence shell. Okay, the base also deprotonates the phenol. This base also deprotonates the phenol, which then attacks, means finally what we are getting is a negatively charged phenoxide. Okay, this phenoxide attacks the carbene, which is electron deficit. Let us see the steps. Okay, so first step, as I have told you, the base abstracts a proton and gives a trichlorocarbon anion. this is a negative charge species. From here the Cl minus leaves, and what we get is a 6 electron species, electron deficit definitely, and it's a carbon. Okay, the next step, as I have told here, as it is narrated, okay, the base again abstracts one proton and a phenoxide ion is formed. Okay, this phenoxide ion, it comes, the negative charge comes to the ortho position, this ortho position, and this one attacks the carbon anion. Now right now what we see here is carbon is having octet, but these 2 electrons which are coming to carbon for attacking, it is from the other carbon, so therefore it is having a negative charge. Since this negative charge takes the proton, okay, and this carbon hydrogen bond comes to the ring and forming the bringing back the aromatic property, and this pi bond breaks accordingly and gives a negative charge to oxygen. Say this will happen in two of the following steps. Okay, in this following steps what we get, okay, once step by step both of the Cl will leave as Cl minus, and we will get the aldehyde group. Just see here, the H has been abstracted, and we are getting the oxygen is having a negative charge. This negative charge comes back to this position to form a pi bond. This pi bond again breaks, and this Cl again leaves as Cl minus. Okay, so what we are getting here, we are getting a double bond here. We are forming a negative, we are breaking this particular double bond. We are forming a double bond. Just see here what has been done. Okay, we have got now only one Cl. Next again the base comes and attacks this position. The pi bond breaks and brings back the aromatic property, means the ring. Okay, alternatively 3 double bond, single bond coming back to the ring, and the pi bond again breaks here. Okay, so what we get here is OH is coming and attacking. So similarly the O minus again comes back to its position, breaks the pi bond from the ring and leaves the Cl minus. The Cl minus leaves. Okay, so therefore to bring back the aromatic property, the OH minus again has an important role, and the OH minus abstracts this particular proton. The double bond comes here, this bond breaks and it comes to the to form a pi bond. The pi bond again breaks. Okay, the pi bond again breaks to bring back the aromatic property, and O becomes O minus. So from this O minus takes one H plus from water. Okay, this water is forming here, the water, and we get what? We get the ortho hydroxy benzaldehyde. Okay, so this is what is, this is being the acid you can give, you may not give. Okay, it will simply speed up the reaction if you are providing acid. That is what is acid workup. Okay, so that is done. Reimer-Tiemann reaction. Remember, the product will never be a para product. It will be mostly an ortho product. Okay, ortho hydroxy benzaldehyde product. Okay, if you are showing here a product like para, what you have to proceed here is this one and show the resonance forming the negative charge in the para position. Okay, so if the question comes like that, that you have to show both the products, you can show accordingly. Either you show, once you show the ortho product, ortho attack, another time you show the para attack. Okay, you already know hydroxy is an ortho para directing group, so there will be no meta product. Let us go to the next topic, that is Kolbe-Schmidt reaction. Kolbe-Schmidt reaction. What is this reaction? Here again carbon dioxide. Okay, it's an electrophile here. Okay, and there is a role of base. Just in place of chloroform, carbon dioxide is the reagent. Okay, just see What is this? The Kolbe-Schmidt reaction is an organic reaction used to convert phenol to to a hydroxy, ortho or para both, okay, to a hydroxy benzoic acid using carbon dioxide gas, base and acid workup. The mechanism begins with the deprotonation of the phenol by the base to form the phenoxide. The phenoxide rearranges to form a carbonyl group, okay, while the aromatic ring attacks the carbon dioxide molecule. The attack can happen from either the ortho or para position, which explains the two possible products and results in the loss of aromaticity of the ring. Means one of the pi bonds will break from the ring. Another deprotonation by the base regenerates aromaticity and produces the phenoxide again. The deprotonation of the phenoxide and that carboxylate ion yields the final ortho and or para hydroxy benzoic acid. Now let us see the mechanism. First of all, the base abstracts the proton to give the phenoxide ion. Now this phenoxide ion can attack from the ortho position, the carbon dioxide, or it can attack from the para position, the carbon dioxide. Okay, so we are getting both the products, ortho and para. Now what we see here is when it is ortho, so same thing is happening in the para. Let me only discuss ortho. So what we are getting is a carboxylate compound and the aromaticity is not there. The one of the ring has broken. The hydroxide again takes the lead and abstracts one proton, brings back the aromaticity and forming a water molecule. This water molecule again has an important role. It will, the phenoxide that is formed here is having two negative charges right now, and it is very unstable, so definitely it will lose one of the negative charges by abstracting proton from water and giving back the phenol, okay, and carboxylate ion. This carboxylate ion again takes a proton from the water molecule and we get orthohydroxy benzoic acid and accordingly para-hydroxy benzoic acid. Let us now go to the next mechanism, freeze mechanism. Okay, freeze rearrangement. It is not a reaction, rather it is a rearrangement. Means the group only changes its position. So what is the product? What is the compounds? It is phenyl ester. The ester breaks this O oxygen and carbon bond breaks, and this particular group, ester group, comes, or you can say the ketonic group rather, from this breaking of this ester. Okay, the ketonic group that is formed, it simply comes from here to here or from this position to the para position, and the age from the this position, there is an age, I feel you understand that, and also there is an age here. This age comes to this position. Simply a kind of rearrangement, means the arrangement is changing. Okay, just like we move a chair from in the position of table, and the table is going to a position of chair, just like that, interchanging its position. So it's a kind of rearrangement. So what are the reagent used here? The catalyst, a Lewis acid. So you understand this is an electrophilic reaction, okay, as initiation. So it is not a reaction, rather it is a rearrangement, but still it will have a role of a Lewis acid or an electrophile. Okay, so the Lewis acid and an acid workup. How the reaction forms. What is the mechanism? The mechanism here is is undergoing electrophilic aromatic substitution. So you have already done it last day, electrophilic aromatic substitution. So first of all, the lone pairs on oxygen. So now we will stop here. In the next video we will finish it.